Hi, my name is Clayton Withers. Today I will be presenting my ongoing research at the University of Arizona's Fluid Mechanics and Instability Laboratory under the mentorship of Dr. Jeffrey Jacobs. This research focuses on efforts to improve imaging techniques on the Rayleigh-Taylor instability in the linear induction motor drop tower. I will start with an introduction to the instability, describe the experimental setup, how we conduct imaging, and various aspects of processing the data. I will then depict the imaging difficulties that the lab has had thus far, and we'll move on to the techniques I have employed to improve imaging with some preliminary results of that technique. Thank you. The Rayleigh-Taylor instability is a pressure and density gradient-driven instability. In the experiment, two fluids of differing densities are stratified with the denser fluid sitting below the less dense fluid. The fluids are accelerated downwards, imparting a net upwards constant body force, depositing energy into the fluid interface. This leads to production of baroclinic torque along the interface, along with vorticity production and a resultant instability. Characteristic spike and bubble structures emerge, which eventually result in a mixing of the interface. It is the growth parameter alpha of these spikes and bubbles that is of primary interest. Here I have listed the vorticity equation. A few assumptions have been made to simplify the equation, including a 2D inviscid and incompressible assumption. This will leave us with only a baroclinic torque term, which governs the Rayleigh-Taylor instability, seeing as how the instability depends on a pressure and density gradient. A constant acceleration body force is applied to the fluids through the means of a device at our lab called the linear induction motor drop tower. This device accelerates an aluminum test sled containing diagnostic equipment and the experimental fluid holding tank. The linear induction motors are the large red structures depicted in the image to the left near the top, and permanent magnetic brakes can be seen near the bottom. The test sled is accelerated in the vertical direction only, establishing the conditions necessary to develop the Rayleigh-Taylor instability. During the course of the experiment, the instability is imaged using a planar laser-induced fluorescence method, or PLIF. A 445 nanometer laser diode provides our light source and is swept through corrective optics across the experimental tank, producing a two-dimensional laser sheet. This laser sheet illuminates a sensitive fluorescent dye laced in the denser fluid, allowing a high-speed camera to capture a two-dimensional cross-section of the instability. The following image sequences depict two previously completed experiments by Matthew Moakler using the mentioned method. The experiments progress in time from left to right, top, then bottom. The left montage depicts an immiscible experiment, the right a miscible experiment. The difference between immiscible and miscible is that immiscible combinations of fluids will not molecularly mix, whereas miscible fluids will mix molecularly. Think oil in water versus milk in coffee. Note that the miscible case becomes very blurry after some mixing has occurred. My research is an attempt to correct this imaging issue. It is largely caused by mismatches in the index of refraction of the experimental fluids. The index of refraction is a material property that governs how light passes through an object. If the index of refraction is uniform across an interface between materials, light rays will travel in a straight line. If the index is non-uniform at the interface, light rays will be bent as they pass through that interface. This is shown in the image at the bottom of the screen. My research focuses on miscible experiments where this concept of differing indices of refraction becomes more of an issue because of the fluid's ability to mix molecularly. The previous method of mitigating the issue was to initially match the two pure fluids indices. However, molecular mixing can cause variation of the property. The material list on screen is for an initially matched fluid pair. You will notice that the index seems slightly mismatched, but that is because it was measured using a sodium line refractometer. If one were to measure the index using a blue light basis that matches our 445 nanometer laser source, you would find that they are more closely matched. I will elaborate more on this index matching in a few slides, but first want to give various reasons why miscible experiments are important and how we can analyze the images that PLIF will produce. Miscible experiments are important for a variety of reasons. To start, even though immiscible physical phenomena do exist, the variety of miscible phenomena are far more prevalent in the events that are of research interest. These include phenomena such as supernova event gas cloud mixing or the inertial confinement fusion process studied at places such as Lawrence Livermore National Laboratory. That alone provides reason to study them in more depth. Other reasons include the fact that most of the literature to date involving Rayleigh-Taylor instability has been conducted in the immiscible regime. This includes many landmark experiments. The miscible case is just lacking in understanding in comparison. Our lab at the University of Arizona has previously done some miscible work, but the results still need verification. Our work has indicated that miscible experiments may yield lower mixing growth rates. However, clearer imaging is required to accurately confirm these findings. Speaking of finding growth rates, how do we accomplish this? The answer lies in concentration data. Currently, concentration is the primary method of establishing mixing region width and is one of the only methods that can serve to indicate local fluid densities. There are not many other methods that can effectively obtain this in an experimental setting. This sample PLIF image depicts concentration data. Since only one fluid is seeded with fluorescent dye, illumination of this dye visualizes that density and concentration. Mathematically, we can solve for the mixing region width using a variety of methods, one of which is listed below. The equation will become a bit clearer on the next slide, but just note that this h value is the only value left that is needed to solve the equation on the right for our growth rate parameter alpha. We already know the acceleration field g, time of the experiment t, and Atwood number a, which is a measure of the density mismatch. So how does this h equation relate to our concentration? Here, a horizontally averaged concentration profile of several time steps of an experiment is shown. The vertical axis depicts the concentration of the calcium nitrate, with 1 being 100% calcium nitrate and 0 being 100% isopropanol. 0.5 would mean that the solution at that horizontal location is a 50-50 mixture of the two fluids. The horizontal axis depicts the distance of the concentration value from the top of the experimental image. As the mixing region develops and grows larger, this concentration profile stretches horizontally. You can see this in the image on the slide. We can calculate the mixing width a variety of ways, including linear regression or an integral definition like the one given in the equation for h on the previous slide, which performs an integration on the curves you see here. Methods will have varying degrees of noise rejection. The integral method is slightly noisy but easy to calculate. We choose a concentration cutoff such as 5% to 95% instead of integrating from -infinity to infinity because in an experimental setting with PLIF images like ours, this will select just the mixing region instead of the entire tank. So now that we understand the experimental setup, how we image, and how we use those images, I want to focus on the difficulties facing the method and techniques to fix those issues. The issues we face in our experiment are largely a product of index of refraction variation. As I mentioned previously, a mismatch of index of refraction will cause bending and diffusion of the light rays coming from the laser, resulting in a blurry image. Previous experiments mitigated this effect by initially matching the indices of the two fluids, but blurriness was still evident in the resulting images. Why is this? The answer is that molecular mixing for the miscible case can alter the index of refraction. What was initially a case of having matched indices becomes a case of mismatch during the mixing event. You can see it here. In the immiscible case, the fluids will not molecularly mix, and therefore won't have exaggerated blurriness. But in the miscible case, you can see that the initially clear images become extremely blurry as soon as mixing near the interface occurs. Let's look at that a little closer to qualitatively see how severe the issue becomes during late-time mixing. Here I have displayed only the miscible case where mixing disrupts the index matching. The instability becomes nearly unintelligible. The question here, can we formulate and analyze this variation of index of refraction? Taking experimental refractive index measurements reveals that the issue can be easily displayed. We can see the refractive index is initially matched for both pure fluids prior to mixing if you look at the far end data points. As mixing occurs, the index changes based on the fluid solution's composition. For this particular combination of chosen fluids, maximum variation occurs at about a 40% mixture value. That is to say that the index will have changed the most when the solution makeup is 40% calcium nitrate, 60% isopropanol. So, we have identified the issue, but can we fix it? The solution is to try and minimize the variation of index of refraction and thus try and compress this curve into an overall flatter shape. The approach taken for this research involves modeling the density and index of refraction as a nonlinear fluid property. This was completed using a similar method to McDougall 1979. The equations for density and index of refraction have a base value equal to the properties of distilled water. This is important because the new fluid combinations will be modified by dilution with distilled water. Both equations have a linear term governing the fluids separately, a nonlinear term governing each fluid separately, and a nonlinear term that characterizes the effect of mixing the two fluids together. Lowercase a, b, c, d, and e are the experimentally determined coefficient values found by measurement. The equations are a function of solute concentration only. Now, how are these fluid property models utilized? I wrote a brute force iterative solver for the purpose of minimizing index variation. There are several important notes here that inform the brute force solver, mitigating the amount of calculations necessary. First, there is a maximum achievable Atwood number for any fluid pair combination. That sets an upper limit on the problem. Second, there also exists a minimum Atwood number for the combination. A very low Atwood number means that there is a very small difference in densities for the fluid combination. Too low of one will prevent any development of the Rayleigh-Taylor instability, since the Rayleigh-Taylor instability is driven by this density contrast. That sets a lower limit for the solver. The solver starts by computing the index and density curves for select useful Atwood numbers. The index variation is then computed for all curves, calculating the difference between the maximum index value and the extrema index value. This gives the total range of index value for each curve. Each curve corresponds to a certain pairing of calcium nitrate and isopropanol concentrations. Finally, the curves and corresponding fluid pairs that best minimize this index delta are chosen. At this point, we have found the best fluid pair candidates. But we have not only found the best fluid pair candidates, we have additionally found a relationship between Atwood number and index variation. For the current fluid combination, increasing Atwood number non-linearly increases the total index variation, resulting in more blurriness. This relationship becomes very pronounced for large Atwood numbers. Here, I have taken the model values for the best candidates at various Atwood numbers. These were the fluid pairs that were modeled and had the smallest value for index of refraction variation. Overlaid onto the discrete model values, I have included a curve fit. This curve fit is a quadratic polynomial which fits the data well. The important thing to note is that the relationship is highly nonlinear. This is possibly the most striking result from this modeling technique. It suggests that very small changes in Atwood number can have very large impact on index variation and thus image quality. We can compare various images that I have produced with experiments. First, I want to show an experimental result for a fluid combination that has not had this minimization effort. This experiment uses the fluid combination stated near the beginning of the presentation. This is a 6-image sequence marching through time for one experiment. The time sequence is left to right, first row, then second row. Notice how the blurriness becomes extreme as soon as there is any significant mixing. Next, we will look at an experiment with similar Atwood value but has been treated with the index variation minimization. Before moving on, I would suggest looking at the bottom row of these images as the blurring has the largest effect at late time. Moving on. Here is a variation minimized trial of similar Atwood number that shows quite a bit of correction to the blurriness. Instability structures are discernible further into the growth than the non-minimized trial. Blurriness does affect the late time growth stages, but not nearly to such a degree as the last example. Continuing, I want to show the effect of minimization of index variation coupled with a sizable decrease in the Atwood number. Much better. The instability is clear and visible well into late-stage growth. Mixing now has a significantly smaller effect on image quality. Individual instability structures are discernible even in the heavily mixed portion of the experimental tank. This improvement has led to images that should be much easier to analyze using our methods. What is really significant here, though, is the heavy dependence on Atwood number. Let's look at a comparison of the two minimized trials. Both of these results were given the index minimization technique, but it is clear that modifying the Atwood number is extremely beneficial to image quality. Let's zoom in a bit further just to show the late growth stage. Here is a singular time step taken at the late stage growth. The improvement is quite remarkable and paves the way for accurate image processing. Because this research is still ongoing, I am not able to report mixing width calculations and growth rate values today, but I can report that my research to this point shows that there are methods that improve image quality for Miscible Rayleigh-Taylor experiments. It also shows that index of refraction variation is nonlinearly dependent on the Atwood number. Now that the technique has been shown to have efficacy, further experiments and processing can be done. This includes conducting an ensemble of experiments for various Atwood numbers to test repeatability and gather more data. Forced experiments can be conducted, which could lead to increasing the usable Atwood range, and possibly most important, miscible results for the growth rate parameter alpha can be compared to the results of the immiscible case. That one is a needed step for validation of past and current experiments. These results also raise an important long-term motivation. Can the imaging issues be mitigated to such a degree as to allow the employment of particle image velocimetry? That would allow further study into the velocity, vorticity, and turbulent kinetic energy of these Miscible Rayleigh-Taylor experiments. So there you have it. This concludes my presentation. If you have questions, please feel free to email me at the given email address below, or stop by the open question session available to the conference. Thank you, and be well.